All right, so formal verification is a great way to up your game when it comes to security. Today I'd like to talk to you about our experience with SCL4. So first, let me provide a little background. We had a small project with a handful of people that started a couple years ago, primarily so we could learn more about formal methods. That project was a success, so we pitched a second project, which we're in the midst of wrapping up right now. From that project, I'm going to talk about three things in particular: booting up the system, CAM keys verification, and our interface with Rust. Then I'll wrap it up with some lessons learned. So these are the objectives we had for our original project. First, we wanted to identify the limitations and benefits of provable security approaches, such as formal verification, that could prove the security of an implementation of something like a protocol gateway converter. We then wanted to perform a study that compared that provable security approach with more traditional cyber assessment methods, things like pen testing and binary analysis. Then we wanted to be able to compare those two approaches and determine a recommended mix that would not only maximize the security coverage, but it might identify security gaps. And those security gaps could provide new thrust for cybersecurity research. So one of the things you might be wondering is, what is a protocol converter gateway? Well, it's a small, inexpensive device that provides a connection to other devices that use different protocols. You might think of it as a person that's a language translator that converts from English to German. SCADA protocol gateways are very common in operational technology or OT environments because they provide connections between actuators, sensors, and other computers so that you can have communication in a control system. One of the things you've got to remember is these devices were originally designed back when OT networks were separate for information technology, or IT. The type of communication they had was pretty much serial, and so they focused on more proprietary or customized protocols. We were going to try and focus on more traditional protocols like the ones at the bottom there. So why did we choose a protocol gateway? Well, in 2020, there was actually a good paper that came out by a security company that did an assessment on these protocol converters. And unfortunately, what they found out is a lot of these devices did not translate things correctly. In fact, one of the devices would take a read command in, it would send a write command out. So that's not very good for security. So what are some of the other shortcomings that software has that could introduce some cyber vulnerabilities? Well, you could have a message that would come into the device that would be malformed, or you could have an improper message translation between the sender and the receiver, just like what I talked about before. You could have a mismatch between the specification and the implementation, which might result in detrimental or unexpected behavior. Or you could have memory safety checks that did not provide adequate coverage to prevent control flow manipulation, like a buffer overflow that might result in remote code execution. I've included some information streams for different resources for vulnerabilities. MITRE's got their common vulnerabilities and exposures, or CVE database. The Department of Homeland Security has their CISA Industrial Control System, or ICS security advisories. Vendors are a great place for information. You can either put out their own security reports, or if you go to their website, look under security, you'll often find information you don't find any other place. Then industry white papers are a good source. So with that motivation, we decided to implement our own protocol gateway that was formally verified. Now, at a high level, what we did is we took a REST implementation and we based that on the protocol specification. That allowed us to take advantage of a lot of the safety guarantees in the programming language. And then we used symbolic execution to do the program correctness part. So that was our original project. Well, let me tell you about our new project. So I've already talked about how we created our own application, a protocol converter, that was formally verified. But with this project, we wanted to expand the security envelope. What I mean by that is that the application would now generate information flows that would interact with other components, either internal, which could be like an FPGA, or external, which might be some unhardened part of a TCP library. So what we decided to work with was SCL4. And to be honest, a big part of it was one of the members of our team, who has a lot of embedded experience, was familiar with the project. And he also knew that there were deployments in real-world projects with this. He also was very familiar with one of the supported platforms, and so he's familiar with the tools and how to interact with the device. It also counted that it was formally verified, it was open source, and it's been around for a while. We deal a lot with industrial control system customers, and that community looks more favorably on technologies that have been around for a while. So let's look at some of the assumptions that we're making right now. If you look at the SCL4 microkernel introduction, or it's commonly known as the white paper, one of the things they talk about is verifying hardware is outside of the scope of SCL4. If you remember on my picture before, the hardware was red, meaning unverified. If you look on the SCL4 website under the proof, again, it's saying that they're assuming that the hardware works correctly. So these are some questions that maybe you can think about as I'm giving the rest of the presentation, because on the last slide, I'm going to come back to these and try and answer them. First, what are the security impacts of the interactions between formally and informally verified components? What is the overfed if you're going to do development, deployment, or integration with existing systems? And can the security guarantees be expanded to user space programs without using a virtual machine? And sort of related to that, can SCL4 run safer languages than C, things like Rust? So now that we've given you some background, we're going to go to the Getting Started page on SCL4, although we're going to take a little bit different approach. Whereas the beginning part of the Getting Started page talks about software, we're focused a little bit more on hardware from what I was talking about before. So one of our first things was, how do we do our test setup? Well, we've got our development system on the left, a monitor on the right, and our supported platform in the middle. Between the two, we've got the serial and HDMI connection. Now, this is just an example of one of our test environments. Again, you've got the two computers, you've got the supported platform, the cabling, and even the USB reader that helps you with the programming. So again, going back to the Getting Started page, but focusing more on the hardware, there's a section that talks about hardware and target supported platforms. Now, if you click on the link, the one that's highlighted is the platform that we worked with. And again, because that was a team member that had experience with this and had a couple in his office. One of the things I wanted to say is that we were aware that this was unverified. So now that we've done the hardware, Let's go back to the Getting Started page up at the top, and let's start looking at the software. In fact, one of the first sentences, it says, there are many repositories. In fact, I've got a little snippet of some of them on the side here. There's actually 42 of them, which is a really good thing. But if you're a newbie and you're a small team and juggling different projects, we decided on the 3 repositories that are listed in the table. We started out with SEL4. We were able to build it. To be honest, we weren't sure what to do with it after that. So then we went to SEL4 test. And we did that pretty much. There was a lot of documentation and thought it would provide some good guidance, but we couldn't get it to boot. So then we went to SEL4 tutorials thinking, that's got some examples. Maybe that'll help us out. And we couldn't get that one to boot either. So then we went back to the supported platforms and we thought, well, let's see if we can go with platforms that might be more popular. Maybe there's some more documentation out there. So we took a look at the Raspberry Pis, the version 3 and version 4. Well, good news, we got Raspberry 4 to boot, but it was only with SEL4 test. So it was only output. We couldn't interact with it. It was about this time that we had a new member join the team that had different skill sets than what we had. When we described to him what we had done and where we were having problems, he had the right response. He said, I know how to fix that. So what he did is he began documenting SEL4. He reviewed a lot of the published documentation about SEL4. It also included our findings. He audited and documented the SEL4 source code, and again documented every step of the way. He then performed binary analysis on our compiled binaries of SEL4, and again documented his assessment. All told, at the end, he has over a 50-page document that gave us a much better understanding of what we had before. Now, because of this, we were able to step back and regroup, and we decided, moving forward, let's focus on these 3 areas, starting with the boot process, then the CAM keys verification, and then Rust. So this is what we used. These are the steps for booting on SEL4 hardware. Now, I'm not going to go through every point here. I use this more for reference and just illustration that we went from just, why is it not booting, to more carefully understanding what part of the boot we might have problems with. We also included down at the bottom the list of the files that we really needed on the SD card to be able to boot it up. So again, what assumptions are we making? If you look on the website for the proof, where it talks about the boot code, it says the proof currently is about the operation of the kernel. It goes on to say, assuming that the boot code was successful. If you look in the SEL4 frequently asked questions, again, it's saying we're assuming that the boot code is correct. So now going back to our process, we went back to some of the good documentation for supported platforms for the Raspberry Pi 4. For example, they tell you about how to do the wiring for the serial connection. They talk about the U-boot commands and tell us that we need a special version to disable the caching. We then went to the SD card setup, and the instructions talk about compiling U-boot and transferring this one file, uboot.env. Well, it turns out that file is now called .config, and from what we could see, it wasn't required. We then went to the section that talked about getting SEL4 onto the Raspberry Pi. It gave us instructions that said you should load the kernel image at this address. Well, unfortunately, that address is reserved on the Raspberry Pi. To be honest, just trial and error, we found if you lose one of the zeros, then it boots. So based on all of our struggles with the boot process, we thought, why don't we come up with a tool that could automate this process? Big picture, what that tool does, first it determines the dependencies, then it goes out, fetches the code, then it builds it, and then it installs it. And by installs, I mean it creates a directory that has all the images on the SD card. Now this is something that we want to give to the SEL4 community to not only use as it is right now, but please feel free to add features to that. We're hoping to be done with the copyright assertion process by November, and you can then find it on the GitHub under Los Alamos National Laboratory. Now the repo is actually called Shrimp, all uppercase with a little r. That's for SEL4 hardware independent make with plugins. All right, so now let me talk to you about CAMKeys verification. Now, CAMKeys is a framework that's aimed at cyber-physical and embedded systems, which typically, as folks have mentioned before, have a static architecture. By that, I mean once you boot up the code, you can't change the components. The CAMKeys system is specified by something called ADL, or a formal architecture description language, which is more input specification for CAMKeys, and includes things like the interfaces, the components, and the connections. When you look in the SEL4 white paper, it talks about the promise of CAMKeys is what is specified in ADL is a faithful representation of the possible interactions. It also has sort of the caveat that the promise depends on enforcement by SEL4, and that the ADL representation is mapped on the SEL4 lower components. So what are the assumptions? Again, if you look at the white paper, which is dated 2020 in June, it says that pretty much it's a work in progress. If you go and look on the website that talks about L4 verified proofs, again, work in progress. Now, I did reach out to one of the SMEs for SEL4 to ask if anything had changed. Again, pretty much said it's a work in progress. So this is an example of one of the CAMKeys files for the app called Adder. If you look, remember I talked about those ADL instructions. It's got some like the components for Adder and client. It talks about connections for shared memory and RPC call. Well, once you run that, you get the output on the right. And this was actually generated by our tool that uses this CAMKeys app as sort of the default one, although you can change it. So now let me talk about our interface with Rust. So as I mentioned before, our protocol gateway converter was implemented in Rust. And it was chosen for that because of the safety guarantees in the programming language. For example, Rust prevents entire classes of memory vulnerabilities like buffer overflows. Now, Rust also uses a number of techniques like the borrow checking and the lifetime scheme to guarantee memory safety. It does not, however, prevent against logic errors like the ones below. But at least you get the memory safety guarantees. So when we started working on this interface between SEL4 and Rust, we went to the web page, and they said the Rust support is no longer supported. And one of the team members did some looking at other projects and just didn't feel like that was the right productive path. So this team member had some really good skill sets. He was really good at writing C. He was really good at writing Rust. And so he had this idea. He said, why don't I write two equivalent programs that when you run the binaries, produce the same output? That was a good idea, but one of his issues was he did not want to include the standard library. Reason for that is that has a lot of operating specific system calls, which would really complicate the implementation. So he wanted to write Rust without the standard library. So he used this resource called the Embedded Rust book. And one of the things he took advantage of is something called the no standard Rust environment. Now, most people used a hosted environment was very much like a PC, but if you used the bare metal environment, then you're not pulling down the standard library. Now you're just depending on the hardware, your crates, and the program to run it in. Another attribute he took advantage of is something called no mangle. And that was to make sure that the Rust compiler didn't mangle the names so that the C program would be confused by what to use. So as far as compiling and linking, what he did is he used to compile it this cargo build command that specifies an ARM64 environment. Then as far as linking it, he was able to specify in CMake that this Rust binary was a static library so that it pulled it in to the C assembly. So with this, he was able to write a C function or a C program that called a Rust function, and it worked. So what are the assumptions here? Well, if you take a look at the assembly, it says that pretty much that for this proof, they're assuming it's correct. So let's finish up with the lessons learned. And again, these are the questions we brought up about halfway through. What are the security impacts of interactions between formally verified and unverified components? Well, SCL4 is formally verified for supported platforms with certain assumptions that are made. When you expand that security envelope and you have information flows that are interacting with other components that are not formally verified, that requires more analysis. It's not just a yes or no. What is the overhead of doing the development, deployment, and integration with existing systems? When we first started this out, we thought getting the system up and booted would just take a couple weeks. It took us a lot longer than that. Well, now we're smarter about it. We've got a tool that can help with the automated build environment. But what that means is that when we look at use cases to use SCL4, we're going to have to think about it carefully and factor that in. Can the security guarantees be expended to user space programs without using a virtual machine? And related, can SCL4 run safer languages than C? We were able to evaluate and deploy SCL4 with a non-traditional program, with Rust. But individual programs are not proven secure because of the way that we did it. So these are the questions that I just went through. I just wanted to finish up and remind you that if you're interested in our automated build tool, take a look at the GitHub under Los Alamos National Laboratory in the November timeframe. And again, it's under the repo name of Shrimp with a little r. Are there questions?
Yeah, you definitely put your finger on a number of pain points, which are some of them quite embarrassing, and I'm not going to argue with any of what you said, except stating that if you started now, your experience would be massively better. We have much easier, approachable ways of deploying SCL4, like the microkit that's just been adopted last week. Last week we also just adopted official Rust support that's fairly mature, so we'll have a talk tomorrow about that. So you...
Maybe ask the setup person for this.
Yeah, so things have been approved, but we do understand that this is really important. And the things like documentation errors in how to bring up a platform is sort of unexcusable, and we really need to make sure that this doesn't happen again. Thanks.
Any other questions?
Were your Rust binaries making any SCL4 specific calls?
To the C, well, the C program was calling it.
More questions? I was just thinking about the bring up instructions for the for platforms. Maybe we should try to automate that. Somehow extract from the instructions what you need to do and actually, run that. I was curious about the sync platform because that is used quite a lot. Do you have the sync platform, the one that you tried the first time? Do you have an after action report of what went wrong there? No.
We haven't got that to work yet.
All right. Okay.
High 4 to work.
Okay. Yeah, we'll have another look at that. Oh, more questions here. Okay.
You showed like a cargo build command, and then the no standard and the no mangle.
Yes.
For using Rust and doing the RPC call, was there anything else special that you needed to do?
There were. There was an extern CPUB command that had to be used. Again, this wasn't my work that I did. I was reading the 50-plus page report. But apparently there's sort of, the registers and parameters have to be in a certain way, and that helps out with that. So.
Is that somewhere, one more question, is that somewhere I could read about on the script?
It's not in there, but what I could do is I could talk to, see if we could include some information on that.
Thank you.
I should advertise Nick's new Rust support again, which has, as opposed to much earlier times, pretty good documentation. It'll tell you how to build. It is very new, as of last week, officially in the foundation, so it's not even linked yet from the website, but the repository exists. So GitHub's SEL4, Rust SEL4 is the repo with links to docs. There was one more question by Brandon, I think.
I think he kind of anticipated it, but I was wondering if that 50-page report was going to be part of the open source release, because it sounds like it would be fun reading.
Yeah,
I
would be.
actually brought it up, but, it's something that probably requires more work because there's parts in there not sure how this happened, but Sandy gave it to me. It's almost like a diary, right? You just sort of oh, this part's going to be complicated. Let me, talk about this. Hang in there with me, So, but I did actually bring that up because it's a very valuable document. So.
Yeah, we can learn from informal papers as well as formal ones.
Yeah, and those those kind of things would be really useful to us to, to improve documentation. Okay, thanks Andy again. Thank you.